there was a time when the universe contained no stars. Space had already been expanding for hundreds of thousands of years. The first atomic nuclei had formed, and light had begun its long passage through a cooling cosmos. But there were no suns, no planets, no galaxies in the form we would recognize, and no points of light scattered across a night sky. About 380,000 years after the Big Bang, the universe cooled enough for electrons to join with atomic nuclei. Hydrogen and helium became neutral atoms, and the bright early plasma faded into a more transparent expanse filled with gas. The afterglow of that transition still reaches us today as the cosmic microwave background. What followed is often called the cosmic dark ages. The name can make this period sound empty, but it was not empty at all. Matter was present everywhere. Hydrogen filled the spaces that would later become galaxies. Helium moved with it. Dark matter, invisible but gravitationally influential, had already begun gathering into uneven concentrations. Across immense regions, the universe was preparing structures that had not yet learned to shine. There were no heavy elements in those first clouds. No carbon, oxygen, silicon, or iron had yet been forged inside stellar cores. The ingredients were almost entirely hydrogen and helium, with a small trace of lithium left from the earliest minutes of cosmic history. Every later complexity was still absent. For perhaps tens of millions of years, gravity worked without any visible display. Slight differences in density slowly deepened. Regions containing a little more matter drew in additional gas. Small dark matter halos became gravitational wells, and within some of them, primordial gas began to collect. Cooling was difficult. Without carbon or oxygen, the gas lacked many of the efficient ways that modern interstellar clouds release heat. Molecular hydrogen became one of the few available pathways, allowing some clouds to cool enough to contract further. Somewhere within that long interval, a cloud crossed a threshold. Its center grew denser, the gas compressed. Temperature and pressure rose. A protostar began forming from material that had never belonged to any previous star. Eventually, hydrogen fusion started in its core, and the first true stellar light entered the universe. Astronomers do not yet know the exact moment this happened. Current models suggest that the earliest stars may have begun forming roughly 100 million years after the Big Bang, though the timing, masses, and environments remain active areas of research. These stars are usually called population 3 stars, a name for a generation made from nearly pristine primordial material. No telescope has yet given us an uncontested portrait of one of these individual stars. Their lives were remote, brief, and concealed within an era whose light has been stretched by cosmic expansion. What we know comes from physics, simulations, traces of early chemical enrichment, ancient stars preserved in the nearby universe, and increasingly deep observations of the first galaxies. Tonight, the path leads toward that missing generation. We will follow the universe from neutral gas into the first collapsing clouds, then into the cores of stars, unlike any shining nearby today. We will see how their radiation began changing the material between galaxies, how their deaths released the first heavier elements, and how later stars inherited what these earliest suns left behind. Before galaxies became familiar structures, before planets could assemble, and before chemistry could build the materials of oceans, stone, air, or living cells, there had to be a first furnace. For a long while, gravity gathered the fuel in the dark. Then one center held enough heat to begin. Long before the first star could shine, the universe had to learn how to gather. Matter was not spread with perfect smoothness. Even in the earliest light, there were slight variations in density, regions holding a little more material than their surroundings, and others holding a little less. Those differences were small, but gravity does not need a dramatic beginning. It only needs time. where matter was slightly more concentrated, gravity drew in more matter. The added mass deepened the pull. Over millions of years, the contrast increased. Invisible clumps of dark matter formed first, creating gravitational basins into which ordinary gas could fall. Dark matter could gather without needing to cool. It did not collide, radiate, or form atoms in the way ordinary matter did. It responded mainly to gravity, and because of that, it began building a framework before any luminous object existed. The first stars would not form in empty space. They would form inside these early halos where gravity had already prepared a place for gas to collect. The gas itself faced a harder task. As hydrogen and helium fell inward, their motion became faster. Collisions converted some of that motion into heat. A cloud that grows hotter resists compression, so gravity alone could not finish the job. The gas needed a way to lose energy. It had to cool while continuing to contract. In the modern universe, clouds can cool through many channels. Atoms such as carbon and oxygen emit radiation. Dust grains absorb energy. Molecules with complex structures carry heat away. None of those helpers were available at the beginning. The first clouds contained almost nothing beyond hydrogen and helium. Atomic hydrogen can cool gas effectively at high temperatures, but many early halos were too small to reach those conditions. In those places, the most important coolant was molecular hydrogen, a simple molecule made from two hydrogen atoms. Molecular hydrogen was rare, but a little could make a large difference. Through a sequence of reactions in the primordial gas, small amounts began to form. When these molecules collided, they could become excited and later release energy as infrared radiation. That radiation escaped, allowing parts of the cloud to cool. The change was gradual. Temperatures remained much higher than those inside many star-forming clouds today. Even so, the loss of heat weakened the pressure pushing outward. Gravity gained ground. Within a dark matter halo, the gas began to settle toward the center. Density increased. The inner region grew heavier than the material around it. Eventually, it reached a point where its own gravity mattered more than the larger halo that had collected it. From there, collapse became more focused. A broad cloud became a denser core. The core drew material from its surroundings. Gas streamed inward along paths shaped by gravity, pressure, and rotation. There may have been turbulence. There may have been several competing condensations. The simulations suggest that some primordial clouds fragmented, while others fed a smaller number of growing protostars. The details remain difficult because the process spans an enormous range of scale. A halo can extend across hundreds of light years, while the forming star at its center is measured on the scale of a solar system. Following every stage requires models that connect large cosmic structure with the behavior of gas at far smaller distances. Still, the general sequence is clear. Gravity gathers the halo. Gas falls inward. Molecular hydrogen allows some cooling. A dense core forms. The core contracts until it becomes opaque enough for heat to remain trapped. At the center, pressure and temperature rise, and a protostar begins to take shape. At first, that protostar is not powered by nuclear fusion. It shines because gravity is compressing it. Material continues to fall onto its surface, releasing energy as it arrives. The young object grows within a surrounding envelope of gas, drawing from a reservoir that may contain far more mass than the star has yet acquired. This is one reason the first stars may have become very massive. Their natal clouds were warmer than most star-forming regions. In the present-day Milky Way, warmer gas has stronger pressure and it tends to collapse into larger pieces. With no dust and few cooling pathways, the fragments could remain large. Material may also have fallen inward at high rates, feeding the protostar rapidly. For many years, models often pictured the first stars as solitary giants, perhaps dozens or even hundreds of times the mass of the Sun. More recent simulations have suggested a wider range. Some early systems may have produced multiple stars. Some stars may have been less massive than the largest first-generation objects once imagined. There was probably no single standard first star. Different halos could have formed stars with different masses, in different numbers, and on different schedules. The first generation may have been a population of varied systems, rather than one simple class of enormous suns, yet they still shared something fundamental. They formed without metals. Astronomers use the word metals for every element heavier than helium. In the first star-forming clouds, those elements were absent. No oxygen had cooled the gas. No silicon had formed dust. No carbon chemistry had shaped the collapse. These stars were built almost entirely from material produced in the first few minutes of the universe. That purity changed how they lived. A star supported by fusion must balance gravity with pressure from its hot interior. The path to that balance depends partly on composition. In metal-free stars, the first stages of hydrogen fusion proceed differently than in stars that contain carbon, nitrogen, and oxygen. The interior must become hotter before certain fusion cycles can contribute strongly. But before any of that can happen, the protostar must finish crossing the threshold into true starlight. As it contracts, the central temperature climbs. Millions of degrees become possible. Hydrogen nuclei move fast enough to overcome their electrical repulsion and join through nuclear reactions. Energy begins flowing outward from the core. The collapse does not simply stop in one instant. The newborn star settles into balance while gas may still be falling around it. Radiation pushes outward. Infall presses inward. The growing star begins changing the cloud that created it. Ultraviolet light heats and ionizes nearby gas. Pressure builds in the surrounding region. Accretion can weaken or be redirected. If several protostars are present, their light and gravity influence one another. The first star is therefore not only a result of its environment, it becomes an active force inside it. For tens of millions of years, the universe had allowed gravity to work almost invisibly. Then, inside one of countless dark matter halos, a dense center crossed into fusion. The light did more than mark a beginning. It began changing the conditions for everything that followed. The first stars did not resemble the sun in every important way. They formed from simpler material, inside hotter clouds, under conditions that no longer exist across most of the universe. Their beginnings were shaped by the absence of carbon, oxygen, silicon, iron, and dust. Their interiors were governed by the same laws of gravity and nuclear physics that govern stars now. But the path toward balance was different. A modern star like the Sun begins life with a small inheritance of heavier elements. Those elements influence opacity, cooling, and the way energy travels through stellar gas. The first stars had no such inheritance. Their matter came almost directly from the Big Bang, mostly hydrogen, a large fraction of helium, and only traces of lithium. That simplicity may have made many of them large. Astronomers once imagined the first generations almost entirely as immense stars, perhaps hundreds of times the mass of the Sun. Simulations now suggest a more varied population. Some may indeed have grown to great masses. Others may have formed with a few tens of solar masses, and some perhaps lower still. In crowded primordial systems, several stars could emerge from one collapsing cloud, competing for the same inflowing gas. Their growth was also shaped by a contest between infalling matter and emerging radiation. As a protostar gained mass, its light pushed against the gas, still trying to reach it. In a cloud containing dust, that pressure can couple strongly to surrounding material. Primordial gas contained no dust, so some matter could continue flowing inward along dense streams, or through a disk even while radiation escaped in other directions. This may have allowed certain first stars to become very massive, before their own feedback finally limited further growth. The range remains uncertain because no confirmed population 3 star has yet been observed as an individual object. The evidence comes from calculations, from the chemical fingerprints left in later stars, and from observations of galaxies so distant that their light began its journey when the universe was very young. Even with that uncertainty, one pattern is likely. Many of the first stars were hotter, brighter, and shorter lived than the Sun. Mass changes nearly everything about a star. A star with more mass has stronger gravity pressing inward. To resist that compression, its core must reach a higher temperature. The hotter core drives nuclear reactions more rapidly, producing enough pressure to hold the star up. This balance can sound restful, but it is not static. A star is always spending fuel to maintain it. In the Sun, hydrogen fusion proceeds slowly enough for the main sequence lifetime to last about 10 billion years. A much more massive star can contain far more hydrogen and still exhaust its usable core fuel in only a few million years. The furnace is larger, but the rate of consumption rises much faster than the fuel supply. For the first stars, this meant that some of the earliest lights in the universe may also have been among the briefest. A star could form after tens or hundreds of millions of years of cosmic preparation, shine for only a few million years, and then disappear in an explosion or collapse. On the scale of the universe, such a life would be almost momentary. Yet during that moment, the star could alter an entire region around it. Its surface temperature may have been high enough to produce large amounts of ultraviolet radiation. These energetic photons could strike neutral hydrogen atoms nearby and remove their electrons. Around the star, a bubble of ionized gas began to grow. The effect was not limited to one small boundary. Ultraviolet light heated the surrounding material. Hotter gas became harder to compress. Molecules that had helped the cloud cool could be broken apart by radiation. In some places, the star's light may have delayed further star formation by dispersing or heating the available gas. In other places, the same radiation may have helped create new structures. An expanding ionization front could press against denser regions, squeezing them. Shocks could gather gas into shells or knots. The first stellar feedback was therefore not a single action with a single result. It could interrupt collapse, redirect it, or prepare another site to contract later. The universe had entered a new phase. Before stars, gravity and cooling controlled the formation of structure. After stars appeared, light became part of the environment. Radiation could travel beyond the halos where it was produced. Heat and ionization could influence matter that had never touched the star itself. The first stars also changed the chemistry around them before they died. Their ultraviolet radiation altered the balance of electrons, atoms, and molecules in nearby gas. Some reactions became easier. Others were suppressed. Molecular hydrogen could be destroyed by certain wavelengths, yet free electrons in ionized or partially ionized gas could later help new hydrogen molecules form. The result depended on distance, density, timing, and the spectrum of the star. There was no universal response. A cloud close to a hot star might be stripped of its cooling molecules. Another cloud, farther away, might receive just enough ionization to change its chemistry without being blown apart. A halo that would otherwise have formed stars could be delayed. A neighboring region might be pushed toward collapse. The first light was not simply illumination. It was a physical force moving through the young cosmos. Inside the stars themselves, fusion began with hydrogen. In the absence of heavier elements, the earliest reactions relied first on the proton-proton chain, the same broad process that powers the Sun. But massive metal-free stars could contract to higher central temperatures, and within their cores small amounts of carbon were eventually created through helium fusion. Once even a trace of carbon existed, The carbon-nitrogen-oxygen cycle could contribute strongly to hydrogen burning. Carbon acted as a catalyst, helping the star fuse hydrogen more rapidly without being consumed in the same way as the fuel. In this sense, the first stars began manufacturing the conditions that changed their own internal behavior. Their structures may have been more compact and hotter than stars of similar mass that contain metals. With fewer heavy elements to absorb radiation, energy moved differently through their interiors and atmospheres. Their light was weighted toward higher energies, making them powerful sources of ionizing photons. If you could have seen one nearby, it would not have looked like a calm yellow point resembling the sun. It would likely have appeared blue-white, intensely bright, and surrounded by a changing region of glowing gas. There would have been no planets with oceans nearby, no dust-rich disk like those around many young stars today, and no familiar chemistry in the surrounding cloud. The scene would have belonged to a universe still near the beginning of its visible history. Yet even that image must be held carefully. Population 3 stars may not all have shared one appearance. Their masses, rotation rates, companions, accretion histories, and environments could have varied. Some may have lived in multiple star systems. Some may have exchanged matter with companions. Some may have rotated rapidly enough to mix fresh fuel into their cores, extending or reshaping their lives. The first generation was likely diverse, even if its ingredients were simple. There is a useful contrast here. The chemistry of the early universe was limited, but the outcomes were not. From hydrogen, helium, gravity, motion, and time, nature produced stars with different masses and destinies. Simplicity at the beginning did not lead to uniformity. It opened several possible paths. While you rest beneath a sky filled with later generations of stars, none of the first suns are visible there now. Their direct light has been stretched, scattered, absorbed, or lost beyond the reach of ordinary sight. The oxygen in Earth's air did not come from the Big Bang. The carbon in living cells did not come from the Big Bang. The silicon in stone, the calcium in bone, and the iron moving through blood all required stars to begin the work of building heavier nuclei. The first stars did not produce every element in its final abundance, and later generations carried much of that creation forward. But the first generation opened the chemical path. Before that path could widen, the stars had to reach the ends of their lives. Their cores consumed hydrogen, helium accumulated. Gravity returned with greater force each time a fuel source weakened. In the most massive stars, new stages of fusion began, each one shorter than the last. The light that had awakened the universe was already preparing to change form. The change began deep inside the star, far below the surface that had been pouring ultraviolet light into the surrounding gas. Hydrogen in the central region was gradually converted into helium. As the hydrogen supply diminished, the energy flowing from the core weakened. Gravity pressed inward more effectively, compressing the center until its temperature rose enough for helium nuclei to fuse. Helium burning created carbon and oxygen. For the first time, atoms with 6 and 8 protons appeared in meaningful quantities inside a star. They had not been present in the cloud from which the star formed. They had not been assembled during the first minutes after the Big Bang. They were new structures built in stellar heat. What happened next depended strongly on the star's mass. A star near the lower end of the first generation's possible mass range might have lived far longer than the large primordial stars usually pictured in models. If any population, 3 stars formed with less than about 80% of the Sun's mass. They could, in principle, still survive today. Searchers for such untouched stars have not found a confirmed example. Their apparent absence is one clue that the first generation may have favored larger masses, though it does not settle the question. For a massive first star, Helium was only the second stage of a much longer descent. When helium in the core became scarce, gravity compressed the center again. Carbon began to fuse. Later came neon, oxygen, and silicon burning. Each stage required a higher temperature than the one before it, and each lasted for a shorter time. Hydrogen burning could continue for millions of years. Helium burning might last hundreds of thousands. The final stages could pass through centuries, months, days, and eventually hours, depending on the mass and structure of the star. The core was building heavier nuclei, while the star's remaining life narrowed. Around the center, fusion continued in layers. Hydrogen burned in an outer shell, helium burned deeper inside. Farther down, carbon and oxygen reactions proceeded at temperatures that would have been impossible during the star's youth. The interior began to resemble a set of nested regions, each containing material shaped by a different stage of nuclear burning. At the center, silicon fusion produced nuclei near iron and nickel. This was a boundary that ordinary stellar fusion could not cross, while continuing to support the star. Fusing light nuclei releases energy because the products are more tightly bound. But near iron, that advantage ends. Building heavier nuclei through fusion requires an input of energy rather than providing a useful return. The core had reached the end of its available path. Gravity had not. Once the central region could no longer generate enough pressure, collapse could begin. Matter fell inward at tremendous speed. Density rose until electrons and atomic nuclei were forced into conditions unlike those in any ordinary gas. In many massive stars, protons and electrons combined to form neutrons and neutrinos. The core contracted to the scale of a city while holding more mass than the sun. The outer layers continued falling, unaware for a brief interval that the center had changed. Then the collapse met resistance. Nuclear matter is difficult to compress beyond a certain point. The inner core stiffened, and the infalling material encountered a sudden change in pressure. A shock wave formed and began moving outward. The shock did not always escape easily. It lost energy as it broke heavy nuclei apart, and as neutrinos carried energy from the collapsing core. Modern supernova models show that the explosion depends on complicated motion, neutrino heating, turbulence, and instabilities around the newborn remnant. Some first stars may have produced successful core collapse supernovae. Their outer layers were expelled into the surrounding halo, carrying carbon, oxygen, magnesium, calcium, iron, and other products of stellar burning. The composition of that material depended on the star's mass, rotation, internal mixing, and the strength of the explosion. In some events, much of the newly formed iron may have fallen back toward the center, while lighter elements escaped. These faint supernovae could leave chemical patterns rich in carbon but poor in iron. Other explosions may have released a broader mixture. The first stellar deaths were probably not identical chemical events. Each one contributed its own pattern to the growing inventory of the universe. In some stars, the collapsing core may have become a neutron star. In more massive cases, gravity may have continued beyond that stage, producing a black hole. FNOR, material that initially moved outward, could reverse direction and fall back. In other cases, the star may have collapsed into a black hole with little visible explosion. A star that died this way could lock away much of what it had created. The first generation, therefore, did not enrich space with perfect efficiency. Some stars scattered their interiors across large distances. Others kept many of their heavier elements behind an event horizon. The chemical development of each early halo depended partly on which kind of ending occurred there. For a narrow range of very high stellar masses, another possibility appeared. Inside an extremely hot core, energetic photons could transform into pairs of particles, an electron and its antimatter counterpart, a positron. Energy that had helped provide outward pressure was converted into particle mass. The core lost support and began to contract. That contraction raised the temperature sharply. Oxygen fusion accelerated through a large part of the core almost at once. Instead of settling into a new balance, the star entered a runaway thermonuclear event. The released energy could reverse the collapse and tear the entire star apart. This is called a pair instability supernova. In idealized models of non-rotating, metal-free stars, such explosions can occur in stars with initial masses roughly between 140 and 260 times the mass of the Sun. Rotation, mass loss, mixing, and uncertain details of stellar evolution can shift those boundaries. Unlike an ordinary core collapse supernova, a full pair instability explosion leaves no neutron star and no black hole. The whole star is dispersed. A single event can eject large amounts of oxygen, silicon, sulfur, and iron group material. The balance of elements has a recognizable theoretical pattern, including a tendency to favor elements with even numbers of protons over nearby elements with odd numbers. Astronomers search for that pattern in very old stars. So far, the evidence suggests that pair instability supernovae were probably not the dominant fate of the first massive stars. Their chemical signature has been difficult to identify clearly in the surviving stellar record. Core collapse explosions, faint supernovae, and black hole forming events may have been more common. At still greater masses, the core could become unstable without producing enough nuclear energy to destroy the star. Collapse might continue directly into a black hole. Under certain early conditions, stars far heavier than the usual population. Three range may also have formed, creating large black hole seeds that later grew inside young galaxies. The first stellar remnants may therefore have included neutron stars, ordinary stellar mass black holes, and perhaps much larger black holes born unusually early. But the material that escaped had the most immediate effect on the next generation. A supernova shock moved through the gas surrounding the dead star. The expanding debris carried newly made elements away from the core and into regions that had once contained only hydrogen and helium. At first, the ejecta were hot and rapidly moving. They swept up primordial gas, forming a shell around the expanding remnant. Over time, the motion slowed, the interior cooled. Metals mixed unevenly with the surrounding material. The mixing was not complete. One part of a halo might receive carbon and oxygen from a single explosion. Another might remain nearly pristine. Dense pockets could preserve the chemical influence of one first star, while neighboring regions carried the combined products of several deaths. This unevenness became a record. Later stars formed from the enriched gas. They incorporated atoms from earlier explosions into their atmospheres, where some of those atoms remain observable today. Astronomers can separate the light of an old star into a spectrum and identify the absorption patterns of individual elements. A star born more than 13 billion years ago can still hold the chemical outline of a predecessor that no longer exists. This practice is sometimes called stellar archaeology. It does not recover the vanished star itself. It examines what the vanished star left inside another. The method requires care. A surviving star's composition may reflect several enrichment events rather than one. Material can mix, fall back, or be added through interaction with a companion. Models of first star explosions also depend on uncertain rotation, internal structure, and nuclear reaction rates. Even so, extremely metal-poor stars provide some of the strongest indirect evidence about the first generation. Their iron content can be thousands or millions of times lower than the Sun's. Some contain unexpectedly large amounts of carbon relative to iron. Others preserve combinations of magnesium, calcium, and lighter elements that can be compared with predicted supernova yields. Each abundance is a fragment of an earlier event. No written history reaches that far. No surviving surface records the flash. The evidence is carried by atoms, passed from one star to another across cosmic time. The supernova also changed how future clouds could cool. Carbon and oxygen provided new channels for releasing heat. At sufficiently low temperatures, their atomic transitions allowed gas to radiate energy more efficiently than primordial material could. Dust, once it began forming from stellar ejecta, offered another powerful route for cooling and fragmentation. A cloud containing even a small amount of heavier material could break into smaller pieces than the clouds that produced many of the first stars. Smaller fragments made lower mass stars more likely. Lower mass stars used their fuel slowly. Some could survive for billions of years, carrying early chemical evidence into the present. In this way, the death of a short-lived massive star helped make possible stars that would outlast entire stages of cosmic history. The first enrichment did not instantly transform the universe. Metals spread through local regions before they became common across larger structures. Primordial star formation may have continued in isolated pockets, while enriched stars were already appearing elsewhere. For a time, two kinds of beginning overlapped. New stars still formed from nearly untouched gas in some halos. In others, supernova debris had already altered the temperature, chemistry, and scale of collapse. The transition from population 3 to later stellar populations was not a single moment. It moved outward from scattered sites of light and death. Within one early halo, the sequence may have taken only a few million years. A cloud contracted, a massive star ignited, its radiation changed the gas. Its core built new nuclei. Then the star ended, and the cloud received material it had never contained before. The first light had become the first ash. And from that ash, the universe began learning how to make smaller stars, longer lives, solid worlds, and chemistry that could continue long after the original furnace was gone. The first stars did not remain isolated for long. They formed inside small, dark matter halos, each one part of a larger pattern of growing structure. Gravity had been building that pattern since the earliest moments when matter began to separate into regions of slightly different density. A halo that formed one generation of stars could later merge with another. Gas flowed inward, the remnants accumulated. New clouds, condensed from material that was no longer chemically pristine. Out of many small beginnings, the first galaxies began to assemble. They were not miniature versions of the Milky Way. They had no broad spiral arms, no settled disk, and no long history written into billions of mature stars. Many were irregular collections of gas, dark matter, young stars, and expanding supernova debris. Their boundaries were not always clear. A small halo might contain only a few sites of star formation. Another might hold several clusters, each turning on at a different time. Nearby systems could approach, pass through one another, and merge. Material was continually rearranged as gravity drew smaller structures into larger ones. Galaxy formation was therefore not a separate event that began after the first stars. The two processes overlapped. Stars formed inside the earliest halos, and the energy from those stars changed how the halos evolved. Their explosions removed gas from some systems. Their radiation heated nearby material. Their remnants added mass to the growing centers. Meanwhile, mergers brought fresh gas and new dark matter into the same regions. The first galaxies were shaped by a conversation between gravity and feedback. Gravity tried to gather. Starlight and supernovae often pushed outward. In a very small halo, a single massive supernova could have a powerful effect. The explosion might drive much of the available gas beyond the halo's weak gravitational reach. Star formation could stop for millions of years while the system waited for material to cool and return. Some halos may never have recovered. Their gas joined the wider space between structures, carrying metals away from the star that created them. Larger halos held their material more firmly. As mass accumulated through mergers and infall, their gravitational wells deepened. Gas that would have escaped from a smaller system remained bound. Supernova shocks still disturbed it, but the material could settle again. New generations of stars appeared, each one forming from gas, altered by those that came before. The change in chemistry could be very small and still matter. A cloud did not need to become rich in heavy elements before its behavior shifted. Tiny amounts of carbon, oxygen, or dust could improve cooling. Denser regions could fragment into smaller clumps. Instead of producing only a few massive stars, a cloud could give rise to a broader range of stellar masses. Some of those stars were large and short-lived. Others were small enough to remain stable for billions of years. The appearance of low-mass stars changed the character of the universe. A massive star burns brightly and disappears. A small star carries its history forward. It preserves elements in its outer layers and may continue shining long after the halo, where it formed, has been absorbed into a much larger galaxy. A few of the oldest stars now moving through the Milky Way may have begun inside those early systems. Their birthplaces no longer exist as separate objects. Over cosmic time, small galaxies merged into larger ones, and their stars were scattered into halos, clusters, and streams. What survives is not the original arrangement, but a population of ancient witnesses. The earliest galaxies may also have contained the first long-lived star clusters. Dense pockets of gas could form many stars in a compact region. Their combined radiation would be stronger than the light of one star alone. Their supernovae could overlap, driving hot cavities through the surrounding medium. Some clusters may have remained gravitationally bound. Others dispersed as gas was removed, or as their host galaxies merged. The oldest globular clusters seen today formed later than the very first stars, but they belong to a related history in which stars increasingly appeared in organized groups, rather than as solitary lights inside small primordial clouds. Within these young galaxies, space would not have felt calm or settled. Gas flowed in from outside along filaments shaped by dark matter. Cold streams could penetrate a halo and feed its center. Supernova remnants expanded through regions already disturbed by earlier explosions. Ultraviolet light carved ionized bubbles into neutral hydrogen. Star formation came in bursts. A galaxy could brighten as a new group of stars formed, then fade as radiation and explosions disrupted the gas. After a period of recovery, another burst might begin. The pattern was irregular, controlled by the supply of gas and the strength of the feedback produced by each generation. This pulsing behavior made early galaxies difficult to predict. Two halos of similar mass could follow different histories. One might form stars efficiently, another might lose most of its gas. A merger could trigger a new episode of collapse, or it could heat the material enough to delay one. The universe was becoming more complex, but not more orderly. As galaxies grew, their stars changed the surrounding space on larger scales. Each hot young star produced ultraviolet photons. Many of those photons were absorbed close to their source, inside the gas of the galaxy itself. Others escaped into the intergalactic medium. Whether the light escaped depended on the arrangement of gas and dust. A galaxy surrounded by dense neutral hydrogen could trap most of its ionizing radiation. A system pierced by supernova-driven channels might allow a greater fraction to pass outward. The escape paths could open and close as the galaxy changed. Beyond the galaxy, every escaping photon entered a universe still dominated by neutral hydrogen. The photon might travel until it encountered an atom. If it carried enough energy, it could remove the atom's electron. The region around the galaxy became ionized. joining the bubbles that had already formed around individual stars. When more galaxies appeared, their bubbles began to grow. At first, the ionized regions were separated by enormous distances. Each one surrounded a source or group of sources. Neutral hydrogen filled most of the volume between them. Over time, the bubbles expanded toward one another. A region containing many galaxies ionized more rapidly than a sparse region. Dense parts of the cosmic web lit first. Voids and remote pockets remained neutral longer. The transformation did not advance like a single wave, moving across space. It unfolded unevenly. One area could be filled with ionized gas, while another remained much closer to the conditions of the Dark Ages. The timing depended on how early galaxies were distributed, how many stars they formed, and how much ultraviolet radiation escaped. Black holes may have contributed as well. Some early galaxies likely contained growing black holes at their centers. Gas falling toward a black hole can become extremely hot and radiate across a wide range of energies. Active galactic nuclei may have helped ionize and heat their surroundings, especially later in the process. But most evidence suggests that stars in young galaxies played the dominant role in supplying the ultraviolet light needed to transform the intergalactic hydrogen. The first stars opened the process. The first galaxies sustained it. This distinction matters because one star could change a local cloud, but a population of galaxies could change the condition of space across hundreds of millions of light years. The universe was no longer waiting for isolated points of light. It was filling with networks of them. From the perspective of any one early galaxy, the larger transformation would have been impossible to see all at once. Its stars shone into nearby gas. Its supernovae pushed material outward. Its dark matter halo merged with neighbors. Beyond that local activity, countless other systems were doing the same thing. Their effects accumulated. Ionized bubbles widened. Heavy elements spread. Low-mass stars survived. Black holes grew. Small galaxies joined larger ones. The first generation had begun as a handful of furnaces inside primordial halos. Now those beginnings were feeding structures that could persist, merge, and carry memory forward. Much later, human beings would look into the night and divide the sky into named patterns. They would use stars to mark seasons, guide journeys, and measure the passage of time. None of those stars would belong to the first generation. Yet the possibility of a stable sky, filled with long-lived lights, began here, when enriched gas started making smaller stars inside the first growing galaxies. The stars visible tonight are descendants in that wider sense. Their composition reflects material cycled through earlier suns. Their host galaxy was assembled from smaller systems. Their light travels through space that was once neutral and opaque to much of the radiation now passing through it. Even the dark regions between visible stars carry the result of that ancient change. They are no longer filled with the same untouched hydrogen that surrounded the first stellar fires. The universe had begun to clear. Not all at once and not everywhere, but galaxy by galaxy, cluster by cluster, photon by photon, the first lights were becoming a connected dawn. The clearing of the universe was not the removal of matter. Hydrogen still filled the space between galaxies. The change was in its electrical state. A neutral hydrogen atom holds one proton and one electron. When a photon carries enough energy, it can separate them. The atom becomes ionized, leaving a free electron moving among positively charged nuclei. If the electron later returns, the atom becomes neutral again. During reionization, these two processes happened continuously. Stars released ionizing photons. Electrons recombined with protons. Dense gas, where particles encountered one another more often, returned to neutrality more quickly than thin gas. The source had to provide not one photon for every hydrogen atom, but enough photons to overcome repeated recombinations as well. This made the progress of reionization depend on more than the number of stars. It depended on where the stars formed, how brightly they radiated in ultraviolet light, how long they lived, and how much of that radiation escaped their galaxies. It depended on the clumpiness of the intergalactic gas and on the rate at which new galaxies appeared. A young galaxy could contain many hot stars and still contribute little if surrounding gas absorbed nearly all of their ionizing light. Another galaxy with fewer stars might have open channels carved by stellar winds and supernovae, allowing a larger fraction of photons to travel outward. The escape fraction is difficult to measure even in nearby galaxies. For galaxies in the era of reionization, it is harder still. The very hydrogen being studied absorbs the radiation that would reveal how much escaped. Astronomers therefore combine indirect observations with models of stellar populations, gas geometry, and galaxy growth. The early universe did not offer a simple answer. Large galaxies were bright enough to observe, but smaller galaxies were far more numerous. A great part of the ionizing budget may have come from systems too faint for earlier telescopes to detect. Each one contributed only a modest amount of light, yet together they may have supplied much of what was needed. Webb has begun revealing many of these early systems in greater detail. Some are compact and actively forming stars. Their spectra can show strong emission from gas excited by young stellar populations. In several fields, observations suggest that groups of faint galaxies helped create ionized regions far larger than the galaxies themselves. The full population is still being counted. Astronomers must estimate how the number of galaxies continues below the detection limit, how rapidly they produce stars, and what fraction of their ultraviolet light entered intergalactic space. Small changes in those assumptions can alter the reconstructed history. Reionization was therefore not only an event to be dated, it was an accounting problem written across the sky. The first line of evidence comes from distant quasars. A quasar is the luminous region around a rapidly feeding black hole. Some can be seen across more than 13 billion years of travel time. Their light passes through the gas between the source and Earth, carrying an imprint of every region it crosses. Neutral hydrogen strongly absorbs light at particular ultraviolet wavelengths. Because the universe expands, the absorption from different distances is stretched by different amounts. When astronomers spread quasar light into a spectrum, they can trace how much neutral hydrogen lay along the path. Near the end of reionization, some quasar spectra show broad regions where very little light arrives. These dark troughs indicate that neutral hydrogen was still present in significant patches. Other sightlines remain more transparent, showing that the transition was uneven from one region to another. A single quasar samples only a narrow corridor through space. Many quasars are needed to build a wider picture, and the most distant examples are rare. Their own intense radiation can also ionize a region around them, complicating the interpretation. Even so, they provide direct evidence that the last stages of reionization were still unfolding when the universe was approaching 1 billion years old. Another record is carried by the cosmic microwave background. That ancient light was released long before the first stars formed. As it crossed the later universe, some of its photons scattered from free electrons created during reionization. The scattering left subtle marks in the microwave background's polarization and reduced some of its original temperature pattern. Measurements by missions such as Planck allow astronomers to estimate the total amount of free electron scattering along the path. This does not produce a detailed map of every ionized bubble. Instead, it constrains the overall timing and duration of the transition. The microwave background sees reionization as an accumulated veil. Quasars see it along individual beams. early galaxies reveal their likely sources. Together, these observations narrow the range of possible histories, though they do not yet select one exact sequence. A future view may come from neutral hydrogen itself. Hydrogen can emit or absorb radio energy at a wavelength of about 21 centimeters under nearby conditions. From the early universe, cosmic expansion stretches that signal to much longer wavelengths before it reaches Earth. The strength of the signal depends on the temperature and state of the hydrogen gas and on the radiation surrounding it. Before the first stars, neutral hydrogen may have absorbed radio background light. As early stars and black holes heated the gas, the pattern changed. When ionized bubbles formed, the neutral hydrogen signal disappeared from those regions. In principle, this creates a three-dimensional record of cosmic dawn. Different radio frequencies correspond to different distances and different moments in time. By observing across a band of frequencies, a radio array can search for the shifting structure of neutral and ionized gas. The measurement is exceptionally difficult. Human radio transmissions, signals from the ionosphere, and bright foreground emission from our own galaxy can overwhelm the faint cosmological pattern. The foregrounds can be thousands of times stronger than the signal researchers seek. Instruments must be calibrated with great precision, and analysis must separate a smooth foreground sky from a weak pattern buried beneath it. Several projects are working towards statistical detections and eventual imaging of this era. Instead of seeing individual stars, they aim to measure the spaces those stars transformed. It is a different kind of astronomy. A visible light telescope gathers photons from luminous objects. A reionization experiment may map where a particular form of darkness remained. That distinction helps explain why the end of the Dark Ages did not mean that every part of space became bright. Most of the universe remained visually dark. The change was that ultraviolet light could travel farther through ionized hydrogen without being absorbed in the same way. Even after reionization, atoms continued to exist. Dense clouds remained neutral. Galaxies held reservoirs of hydrogen. Electrons and protons recombined wherever conditions allowed. But across most of the diffuse intergalactic medium, the balance shifted toward ionization and stayed there, maintained by the accumulated radiation of galaxies and active black holes. The bubbles eventually connected. Their boundaries met across filaments and voids. Narrow neutral barriers broke into islands. The remaining islands contracted into regions where gas was denser or sources were sparse. The topology may have resembled foam at first, then a web of joined cavities, and finally scattered neutral remnants inside a mostly ionized expanse. No observer watched this in from outside. There was no single horizon from which the whole process could be seen. Every early star occupied one small volume. Every galaxy cleared only its surroundings. The global transformation emerged from countless local actions that never knew they were part of a cosmic transition. There is a human echo in the way we have reconstructed it. One instrument reads ancient microwave polarization. Another separates the spectrum of a distant quasar. Infrared telescopes count faint galaxies. Radio arrays listen for hydrogen across landscapes, chosen for their distance from transmitters and cities. The evidence arrives in different forms collected by people who may never observe the same object or use the same wavelength. Only when the measurements are brought together does the larger shape begin to appear. By roughly the end of the universe's first billion years, most intergalactic hydrogen had become ionized, though the exact timing varied across space and remains an active field of study. The cosmic dark ages had ended not through one sunrise, but through overlapping generations of stars and galaxies. Their light changed the path available to later light. Photons from younger stars could travel across expanding distances. Galaxies became visible to one another over broader regions. Radiation backgrounds grew. The universe moved toward the transparent state in which astronomy itself would eventually become possible. The first stars could not know what their light was opening. They burned inside small halos, lived briefly, and disappeared. But the space between them remembered. The earliest stars are gone, but the search for them continues in several directions at once. Astronomers look outward toward galaxies whose light began traveling when the universe was young. They also look nearby into the oldest stars of the Milky Way, where ancient chemical patterns may preserve the influence of vanished stellar ancestors. These two approaches meet across an immense distance. One tries to observe the first generations near the time they lived. The other studies what remained after their deaths. Looking directly into cosmic dawn requires infrared astronomy. Light emitted in visible and ultraviolet wavelengths by early stars has been stretched by the expansion of the universe. By the time it reaches Earth, much of it arrives in the infrared. The farther the source, the greater the stretching. This shift allows astronomers to estimate distance by identifying recognizable features in a spectrum and measuring how far their wavelengths have moved. For the earliest galaxies, one especially important feature is produced when neutral hydrogen absorbs light below a particular ultraviolet wavelength. In a distant spectrum, the point where the light suddenly weakens can reveal how strongly cosmic expansion has shifted it. Yet a distant galaxy is not the same as an individual first star. A telescope may collect the combined light of thousands or millions of stars. Gas around them can add bright emission lines. Dust, when present, can absorb and re-radiate energy. A growing black hole may contribute its own radiation. The resulting spectrum is a mixture. Astronomers must separate those possibilities carefully. A galaxy containing metal-poor stars can resemble one containing truly metal-free stars in some observations. A very young stellar population may emit intense ultraviolet radiation, even if it belongs to a later generation. Gas surrounding the stars can strengthen certain spectral lines and make the system appear more unusual than the stars alone would suggest. This is why claims of the first direct detection require caution. The desired evidence is not simply a very distant object. It is a combination of distance, age, chemical composition, and stellar behavior that cannot be explained more convincingly by later stars, gas, dust, or an active black hole. First stars are expected to leave distinctive effects in the light of their host systems. Because many may have been hot and massive, they could produce large numbers of energetic photons. These photons would ionize surrounding hydrogen and helium. When electrons later recombined with atomic nuclei, the gas could emit light at specific wavelengths. One possible clue involves ionized helium. Removing an electron from singly ionized helium requires more energetic radiation than ionizing hydrogen. A strong helium emission line, together with weak or absent signatures from heavier elements, could point toward an extremely hot and chemically primitive stellar population. But this clue is not unique. Accreting black holes can also generate hard radiation. Certain later generation stars may contribute. Shocks in gas can produce some of the same features. A single line, even if measured clearly, cannot by itself prove that population 3 stars are present. The surrounding spectrum matters. So does the shape of the galaxy, the intensity of its radiation, the behavior of its gas, and the possibility that several sources are blended together. Gravitational lensing can help. A massive galaxy cluster bends space around it. Light from a more distant object passing near the cluster can be magnified, sometimes by a large factor. The distant galaxy may appear stretched into an arc or repeated in several images. This natural magnification can reveal objects that would otherwise remain too faint. In rare cases, a single star or compact stellar system may be amplified when its light passes through a particularly favorable arrangement of mass. Smaller objects within the lensing cluster can create additional magnification, causing a distant source to brighten temporarily. Such events offer a possible path toward individual stars at great distances. Even then, identifying the star's generation remains difficult. Brightness can help estimate mass, but lensing strength is uncertain. Temperature can shape the spectrum, but the surrounding gas modifies it. A star may belong to an early, metal-poor population without being truly primordial. The distinction between very old and first is narrow in time, but profound in chemistry. First stars formed from material untouched by earlier stellar interiors. Every generation after them formed from gas that may have contained at least a trace of newly made elements. That trace can be hard to detect across billions of light years. For this reason, nearby stellar archaeology remains one of the most useful tools. The Milky Way contains stars with extremely low abundances of iron and other heavy elements. Many reside in the galactic halo, moving on extended orbits that carry them far above and below the disk. Some belong to small satellite galaxies or ancient stellar systems later absorbed by the Milky Way. Their surfaces can preserve the composition of the gas from which they formed. When light from one of these stars passes through a spectrograph, dark absorption lines reveal the elements in its atmosphere. The depth and shape of each line allow astronomers to estimate abundance. Iron is commonly used as a reference because it produces many measurable features. But iron alone does not tell the full story. A star with very little iron may contain relatively large amounts of carbon. Another may show unusual ratios of magnesium, calcium, sodium, or heavier elements. These combinations can be compared with models of supernova explosions. The goal is to work backward. Given the elements inside a surviving low-mass star, what kind of earlier star could have produced them? A faint supernova in which much of the iron-rich material fell back into a black hole may leave one pattern. A more energetic explosion may leave another. Rapid rotation can change internal mixings and the production of certain nuclei. Binary interaction may later alter the surface of the surviving star. Every reconstruction contains uncertainties. The ancient star may have formed from gas enriched by more than one explosion. The ejecta may have mixed unevenly. Some elements may be difficult to measure. Models depend on nuclear reaction rates and the internal structure of stars that cannot be observed directly. Still, the method has revealed something important. The first generation was probably not represented by one mass and one kind of death. The chemical record points toward diversity. Some vanished stars appear to have produced carbon-rich, iron-poor ejecta. Others contributed different balances of lighter and heavier nuclei. The range suggests that the first stellar population included varied masses, explosion energies, rotation, histories, and remnants. The search also continues for a surviving population 3 star. If one formed with sufficiently low mass, it could burn hydrogen slowly enough to remain alive today. Such a star would contain almost no elements heavier than helium unless later material had collected on its surface. No confirmed survivor has been found. This absence may mean that the first stars rarely formed at low mass. It may also mean that survivors are extremely uncommon, difficult to distinguish, or hidden in regions that have not been searched deeply enough. A small star can spend more time in existence than the structures around it. Its birth galaxy may merge into another. Its companions may be lost. Its orbit may change as larger systems assemble. After more than 13 billion years, it could move through the halo of the Milky Way as a faint point among countless others, carrying a composition older than the galaxy that now contains it. Surveys search for candidates by first measuring colors and broad spectral features across large areas of sky. Promising stars are then observed with higher resolution instruments capable of separating finer chemical signatures. The work is patient. A large survey may identify millions of stars, while only a small number are metal poor enough to justify detailed follow-up. Of those, even fewer approach the chemical conditions expected near the beginning of stellar history. Each candidate becomes a test. Does its spectrum show iron? Does it contain carbon? Are the apparent abundances affected by temperature, gravity, or motion in the atmosphere? Could it have received material from a companion? Could its surface have been altered during its own evolution? The oldest evidence often requires the most careful handling. There is another route through supernovae themselves. If a first-generation star exploded at a sufficiently high redshift, its transient light might briefly outshine its host environment. Different explosion mechanisms would produce different brightness patterns, durations, and spectra. A pair instability supernova could remain luminous for a long interval in the star's own frame because of the large amount of radioactive material produced. Cosmic expansion would stretch that interval further for an observer on Earth, but such events are expected to be rare. They would also be faint after crossing so much distance. Their light could be confused with other kinds of supernovae or with variable activity near black holes. Detecting them would require repeated observations of the same deep fields, followed by careful comparison over months or years. The sky at great distance does not offer its history in one image. It must be revisited. A source that appears once may be a transient. A source that slowly brightens and fades may reveal an explosion. A source that remains steady may belong to a galaxy or an accreting black hole. Time becomes another instrument. Across all these searches, astronomers are trying to connect scales that seem almost incompatible. A nuclear reaction inside one vanished star changes the abundance of an element. That element becomes part of a later cloud. The cloud forms a low-mass star. The star survives for billions of years. Its light enters a telescope. A dark line in a spectrum becomes evidence of an event that occurred before the Milky Way had taken its present form. The chain is long, but it is physical at every step. Nothing in it requires the first star to remain. Its influence is enough. The same is true in the distant universe. An early galaxy may be too small to resolve into individual stars, but its gas responds to their radiation. Its spectrum carries the shape of their temperatures. The ionized region around it records the energy they released. The first stars can be approached through what they changed. That may be the most fitting way to find them. They were the generation that altered everything around them, while leaving almost no direct survivors of their own. Their light crossed the early universe. Their atoms entered later stars. Their remnants joined growing galaxies. And their absence became a pattern that modern instruments are learning slowly to read. The first stars changed more than the brightness of the universe. Before they appeared, nearly every ordinary atom belonged to a remarkably limited inventory. Hydrogen was abundant. Helium followed. Lithium existed only in traces. The universe had structure, motion, temperature, and gravity, but its chemistry could not yet build most of the materials now found in planets, atmospheres, oceans, or living cells. The first stars opened that possibility. Their importance does not rest on one discovery or one moment of illumination. It rests on a sequence of transformations. Primordial gas became a star. Fusion changed the contents of the stellar core. The star released radiation into surrounding space. Its death scattered some of its newly formed elements. Enriched gas cooled in new ways. Later, clouds divided into smaller fragments and produced longer-lived stars. Each stage prepared the next. This is one reason the first stars are difficult to separate from the history that followed them. They existed briefly, but their influence continued through every later generation of stellar formation. A cloud containing carbon and oxygen behaves differently from a cloud containing only hydrogen and helium. It can radiate energy through additional atomic transitions. If dust grains are present, they can absorb heat from collisions and release that energy as infrared light. Cooling allows gas to contract into denser and smaller regions. The characteristic mass of newly forming stars can then decrease. Not every enriched cloud produces a solar-type star, and not every metal-free cloud produces an immense one. Nature allows a range of outcomes, but the addition of heavier elements widened that range. It made stars like the Sun and stars much smaller than the Sun increasingly common. Long-lived stars created something the first generation could rarely provide: time. A star with a fraction of the Sun's mass can shine for far longer than the present age of the universe. Its light changes slowly. Its surroundings may remain stable over immense intervals. Planets, when they form, can orbit through billions of years of chemical and geological development. The first stars did not possess that kind of patience. Many consumed their fuel rapidly. Their role was not to remain. Their role was to alter the conditions under which remaining became possible. The first heavy elements were only a beginning. Carbon and oxygen emerged inside stellar cores. Supernovae created and dispersed additional nuclei. Later stars inherited those elements and continued the process. Some produced nitrogen, others built heavier nuclei through repeated episodes of fusion and neutron capture. Exploding stars, merging neutron stars, and aging stellar envelopes all contributed to the chemical abundance found in the universe today. No single generation made everything. The history of matter is cumulative. An atom of carbon may form inside one star, pass into a gas cloud after that star's death, become part of another star system, enter a planet, and later move through the atmosphere, ocean, rock, or living tissue of that world. The atom does not carry a record that can be read directly. Its identity is the record. Carbon could not have existed before stars learned to fuse helium. Oxygen could not have filled planetary minerals before stellar interiors created it. Iron could not have entered rocky cores before high-temperature nuclear burning and stellar explosions made it available. The first stars began this chain, but they did not know where it would lead. There is no direction built into stellar evolution. A star does not manufacture carbon in order to prepare a planet. A supernova does not disperse oxygen with an intention toward oceans. These events follow pressure, temperature, gravity, and nuclear physics. Yet when enough events accumulate, new possibilities appear. Chemistry becomes more varied. Dust forms. Rocky material becomes available. Planetary systems can contain solids as well as gas. Complex molecules can arise in cold clouds and young disks. The universe does not plan these changes, but it retains them. Every generation begins with material altered by earlier generations. The same inheritance-shaped galaxies. The earliest galaxies were poor in heavy elements and easily disturbed. Their gas was heated by young stars and expelled by supernovae. Over time, larger systems gathered more material and held it more securely. Their star-forming regions became enriched by repeated cycles of birth and death. A galaxy slowly became an ecosystem of matter. Gas collapsed into stars. Stars returned energy and atoms to the gas. New stars formed from the mixture. Black holes consumed some material. Explosions drove other material into halos and intergalactic space. Mergers brought in fresh gas and ancient stars from smaller systems. The Milky Way is still participating in this cycle. Its disk contains clouds where new stars are forming now. Its halo contains old stars that may have originated in galaxies absorbed long ago. Supernova remnants move through interstellar gas. Heavy elements continue passing from one structure to another. The process began before the Milky Way existed. When you look at the sky from Earth, the stars appear separated by dark intervals. The pattern can feel fixed, as though each point occupies its own place and has always belonged there. But the stars are connected by history. Their material has been exchanged across generations. Their galaxy was assembled through mergers. Their light crosses gas altered by earlier radiation. Even stars born far apart may contain atoms produced by similar kinds of ancient explosions. The connection is not visual, it is physical. Long before human observers named the constellations, the matter in those stars had already passed through earlier forms. Long before maps of the sky were drawn, gravity had gathered small halos into galaxies. Long before anyone could ask where the elements came from, stellar interiors had been answering through their own evolution. Across generations of human life, the night sky seems nearly unchanged. A parent can point out a bright star to a child. Many years later, that child may stand beneath the same seasonal sky and point toward the same region for someone else. The stars have moved, but not enough for ordinary sight to notice. Their apparent constancy allows memory to cross from one life to another. The first stars offered no such long human continuity. They existed before Earth, before the Sun, and before the elements needed to build either one. But a different kind of generational thread leads back to them. It passes through matter instead of stories. The calcium in bone belongs to a history of stellar fusion and explosion. The oxygen drawn into the lungs belongs to a history of stars that enriched the gas from which the solar system formed. The iron inside blood belongs to nuclear processes that began in stars and violent stellar endings. Not every atom in a human body came from the first generation. Most were produced later, after many cycles of stellar evolution. Still, without the first transition from primordial gas to enriched gas, none of those later cycles could have unfolded in the same way. The first stars stand near the beginning of the material ancestry. This does not make the universe smaller or more centered on human life. It makes human life part of a longer physical continuity. The body resting now is made from matter that has crossed several environments. Some atoms were once inside stars. Some spent time in interstellar clouds. Some became part of earlier organisms, oceans, minerals, or air before entering their present arrangement. Nothing in that history moved in a straight line. Matter circulated. Structures formed and dissolved. Atoms joined one system, left it, and entered another. The universe awakened through recycling, as much as through creation. Even the first stars were assembled from older material in a broader sense. Their hydrogen and helium came from the early universe. Gravity gathered what already existed. Fusion rearranged it. The stars did not create matter from nothing. They gave existing matter new forms. That pattern continues. A molecular cloud does not begin as an empty space. It gathers gas shaped by previous stars. A planet does not begin with untouched ingredients. It forms from a disk containing a chemical record. A living system does not stand outside this history. It reorganizes matter that has already traveled for billions of years. The first stars therefore mark a threshold rather than an isolated beginning. Before them, the universe had matter but little chemical variety. After them, it had inheritance. Every later star could receive something from those before it. Every later cloud could carry traces of previous heat, radiation, and nuclear change. Every later galaxy could grow from systems that had already begun producing light. The threshold was crossed many times in many places. There may never have been one first star whose identity can be recovered. Several halos may have formed stars within a narrow span of cosmic time. The earliest generation may appear across regions too distant from one another to exchange light before their brief lives ended. The beginning itself may have been distributed. That does not lessen it. Across a universe still filled with neutral gas, separate clouds reached the conditions for fusion. One after another, they became sources of heat, radiation, and new elements. Their combined influence changed the direction of cosmic history. The simple universe did not disappear. Hydrogen remains the most abundant element. Helium remains common. Gravity still gathers matter. The oldest laws continue operating beneath every layer of later complexity. What changed was the number of possible outcomes. From a few ingredients came stars. From stars came new elements. From enriched clouds came smaller and longer-lived suns. Around some of those suns came planets. On at least one planet, matter became capable of studying the light that began the sequence. Tonight, the first stars remain beyond direct recognition. No familiar constellation contains them. No surviving image shows their surfaces. Their names were never recorded because they disappeared billions of years before naming began. But their work is present in every direction. It is carried by the chemistry of stars, by the transparency of intergalactic space, by the growth of galaxies, and by the materials resting here on Earth. The first light did not simply travel outward, it entered everything that came after. The universe did not awaken in a single instant. There was no boundary where darkness ended everywhere and light began everywhere at once. The first stars appeared in separate places, inside small halos, divided by distances their radiation had not yet crossed. One cloud reached the conditions for fusion, then another. Across the expanding universe, isolated sources began shining into regions that had never received starlight before. Most of those stars lived briefly. Their light moved outward while their cores moved rapidly through the stages of nuclear burning. Some ended in explosions, some collapsed into black holes, some scattered carbon and oxygen into their surroundings, while others carried much of their newly made material inward with them. No single ending defined the first generation. That uncertainty remains part of the story. Astronomers do not yet know the full range of masses these stars possessed. They do not know how often they formed alone, how often they formed in pairs or groups, or how many survived long enough to influence neighboring halos. They do not know precisely how much of their ionizing radiation escaped into intergalactic space. Even the date of the first ignition remains an interval rather than a moment. The earliest star may never be identified. Its light may have been absorbed nearby. Its host halo may have merged into a larger system. Its atoms may have passed through several generations of stars before becoming part of structures that still exist. The beginning may remain known only through its consequences. That is not unusual in astronomy. A black hole is often studied through the motion of nearby matter. A planet can be discovered through the faint dimming of its star. Dark matter is mapped through gravity rather than light. The first stars also reveal themselves indirectly. They left ionized gas. They left heavy elements. They left black holes and expanding remnants. They changed how later clouds cooled and how later stars formed. Their presence is written into a universe that became different after they appeared. Future observations may narrow the uncertainties. Deeper infrared spectra may reveal galaxies containing extremely primitive stellar populations. Gravitational lenses may magnify sources too faint to detect alone. Radio measurements may trace neutral hydrogen through the period when the first luminous objects began heating and ionizing their surroundings. Ancient stars in the Milky Way will continue offering another path. Each newly measured atmosphere can preserve an elemental pattern older than the galactic disk. Some patterns may point toward faint supernovae. Others may suggest rapidly rotating stars, energetic explosions, or enrichment by several sources. The record will remain incomplete. A star's chemical abundance is not a photograph of the event that produced it. It is the result of fusion, explosion, mixing, cooling, collapse, and and later stellar evolution. Researchers must move backward through that chain, comparing what is observed with what physics allows. Different explanations may fit the same evidence. New measurements may remove one possibility and reveal another. The first stars belong to a part of cosmic history where certainty grows gradually. This makes them no less real. Long before direct observation became possible, their existence followed from the chemistry of the universe. The Big Bang produced abundant hydrogen and helium, but very little else. Heavy elements had to be made later. Some generation of stars had to be first. Those stars did not need to resemble the sun. They needed only to gather, ignite, and begin changing their surroundings. From that simple requirement came a transformation large enough to reach the present. The space between galaxies became ionized. The first enriched clouds appeared. Low-mass stars became easier to form. Galaxies acquired longer histories. Solid material became available for planets that would not exist until much later. The distance between those first stars and the world beneath you is more than a distance measured in light years. It is a sequence of physical inheritances. Hydrogen entered early stars. Fusion produced carbon and oxygen. Explosions carried those elements into gas. The gas entered later stars and planetary systems. Some of it became part of the cloud that formed the sun. Some became Earth. That chain does not imply that the first stars were leading toward this planet. Most enriched regions never produced a world like Earth. Most stars did not become part of the solar system's ancestry. The universe followed countless branches, and only one small branch contains the place from which this history is now being considered. Still, the connection is material. The night sky is not separate from the body observing it. Both belong to the same history of matter changing form. The stars above are later generations, carrying elements inherited from earlier ones. The ground below contains atoms produced in stars that died before the sun formed. The air carries oxygen, made possible by stellar nucleosynthesis, and later transformed by life on Earth. Resting here, you occupy a structure that the early universe could not have assembled. The first cosmos had the laws needed to make such a structure, but not yet the materials. Those materials had to be prepared over time. Stars had to live. Stars had to die. Galaxies had to gather and mix what remained. The path was long enough to cross most of cosmic history. And yet the beginning of that path was physically modest. A cloud of hydrogen and helium contracted inside a small halo. Molecules carried away a little heat. Gravity continued drawing matter inward. The center became dense. The center became hot. Fusion began. There was no audience for that first light. No planet turned beneath it. No eye received it. No instrument separated it into wavelengths. The star shone into gas and space, and that was enough. Light does not require a witness to change what it touches. Ultraviolet photons ionized atoms. Heat altered the motion of gas. Radiation pushed against infalling matter. The star's core built nuclei that had never existed there before. Its life was brief by the standards of smaller stars, but duration was not the measure of its importance. The first stars mattered because the universe retained what they did. It retained their elements. It retained their remnants. It retained the structures their radiation helped shape. Nothing returned fully to the state that came before them. The cosmic dark ages became a finished chapter of physical history. Even though much of the universe remained dim, darkness continued, but it was no longer untouched. Somewhere within it, light had already begun crossing. That light has traveled for more than 13 billion years through an expanding universe. Much of it no longer arrives in wavelengths human eyes could see. Some was absorbed and re-emitted. Some scattered from gas. Some may still be moving through regions no observer has measured. Its source may be gone. The journey continues anyway. Beyond the window, the visible stars belong to a later universe. They shine with elements inherited from predecessors. Around some of them, planets move through long orbits. Between them lies space that was once transformed by the first generations of radiation. Nothing in the sky marks the exact location where the earliest star ignited. There is no constellation for it. There is only the universe that followed. As the night deepens, the long sequence can recede from thought. The first cloud can return to the distance where it belongs. The first furnace can burn without needing to be pictured. The early galaxies can continue gathering far beyond the edge of ordinary perception. Here, the present remains small and steady. Above it, later starlight crosses the atmosphere and reaches the ground. Some photons end their journeys on rooftops, water, leaves, and closed windows. Others enter telescopes. Others continue past Earth, into the space beyond. The first light began a motion that never required completion. It only needed to begin. And somewhere beyond every visible star, the first dawn is still traveling.